Welcome to today's Explainer. I am your host, and today we're venturing into the very heart of the atom. Now, if you've studied basic physics, you already know the classic model, right? A nucleus in the center with electrons orbiting around it like tiny little planets. It's clean, it makes sense. But when modern quantum mechanics introduces Werner Heisenberg's incredibly abstract matrix math, well, that intuitive picture completely vanishes. So today, our goal is to build a bridge. We're going to connect that familiar, intuitive planetary model right to the abstract world of matrix mechanics and show you how these historical ideas actually still hold the key to understanding modern physics. But before we start juggling heavy formulas, what if I told you that the famous quantum leap, the idea that an electron just instantly teleports from one energy level to another, might actually be holding back our understanding? What if, and bear with me here, instantaneous quantum leaps don't even exist? Just keep that thought in mind as we dive in.
Here is our roadmap for today. 1. From the planetary model to matrices. 2. Canceling quantum jumps. 3. Visualization, Sommerfeld ellipses. 4. Commutant and contramutant transitions. 5. Birth and acceleration of a photon. And finally, 6. The philosophy of virtual orbits.
From the planetary model to matrices.
Okay, let's dive into this. We're starting with Niels Bohr's classic 1913 planetary model. Honestly, it's elegant, and it brilliantly explained the discrete energy levels of hydrogen. From it, you could easily calculate the exact color of the light an atom emitted. But it had a fatal flaw, one that gets skipped in a lot of basic lectures. It was completely blind to the intensity or the brightness of those spectral lines. Think of it like knowing the precise color of a firework you're about to launch, but having absolutely no idea how big the explosion's going to be. This crucial gap in the math is what literally triggered the collapse of the old theory.
Section 2. Canceling quantum jumps.
So here is the ultimate what-if scenario. Bohr's instantaneous jump was essentially pure magic teleportation. It's like vanishing from the top of a staircase and instantly appearing at the very bottom. Poof. But what if we replace that with Max Born's idea? Born suggested that a transition is actually a continuous change of quantum action. Think of it more like smoothly sliding down a ramp instead of teleporting. By making this process continuous, we can suddenly use classical calculus right in the heart of a quantum system. We literally turn magical teleportation into a mathematically trackable process, a real game changer.
And this brilliantly illustrates why we desperately needed this new math. Just look at the Grotrian diagram for helium. It looks like a highly complex spreadsheet or some tangled, chaotic web of energy states. It is a far cry from Bohr's simple, neat little concentric circles, right? Real atoms have complex spectral lines that basic circle geometry simply cannot explain. We absolutely needed quantum mechanical matrix elements to calculate and actually predict these intricate transitions.
Section 3. Visualization, Sommerfeld ellipses.
Now, to avoid drowning in all that heavy calculus, we turn to Arnold Sommerfeld. He essentially modified Bohr's circles into elliptical orbits. And the absolute genius here is that we can use the geometry of these ellipses, ranging from wide and round to incredibly narrow, needle-like shapes, to visually scale quantum mechanical matrix elements. The geometry itself literally dictates how likely and how bright a transition is going to be. It gives us a tangible, physical, visual map for math that is otherwise totally invisible. Section 4. Commutant and contramutant transitions.
So, the crucial point is how the electron actually moves. We have two main categories here. First, commutant transitions. These happen when quantum numbers change in the same direction. Geometrically, it's a constructive, neat inward spiral that stays entirely within the initial orbit, and boom, it results in high-intensity bright light. But then you have contramutant transitions, which are destructive. Here, the electron takes this bizarre, awkward, extraorbital path outside the larger ellipse just to reach the smaller one. Because of that weird path, it partially cancels out the radiation, leaving us with a very dim line. Intuition wins again.
Section 5. Birth and acceleration of a photon.
Let's move to and see how this builds, because this next part completely shatters everything we usually assume. A photon doesn't just magically pop into existence traveling at the speed of light. No way. First, the continuous change in action begins. Then the photon is essentially born in the atom's near zone, and amazingly, its initial speed is proportional to the electron's speed, not the speed of light. It actually accelerates within this near zone, only hitting the ultimate cosmic speed limit of light, c, as it fully exits the atom. Crazy, right?
Section 6. The philosophy of virtual orbits. Now, what's really interesting about this slide is how we resolve a massive historical paradox. Back in the 1920s, Heisenberg famously threw the whole concept of orbits right in the trash. He argued that physics should only rely on real, observable data, like spectral lines. Yet, we literally just used orbits to successfully predict that exact data. So what's the secret? Well, we no longer view them as physical wire rings floating out there in space. Instead, we treat them as virtual orbits. They are purely mathematical tools that just happen to yield perfectly real, observable data.
To sum it all up, virtual orbits are mathematically equivalent, unobservable entities, much like Schrödinger's wave functions, that give us intuitive power over quantum mechanics. By completely abandoning that magic quantum jump dogma, we've successfully bridged the gap between old-school visual geometry and modern abstract computational power. And that leaves us with a pretty profound question to chew on. If a theoretically wrong historical model can be this unbelievably useful for uncovering the truth, what other concepts in modern science are just sitting there, waiting to be brilliantly reinterpreted? Thanks so much for exploring with us today.